You want to put it up here? Go for it. It sounds like you're doing it. What are you not doing?
No, I'm doing it. I'm just looking at it.
So what we're saying is if something is equal to that thing, minus that thing is equal to that, right? So replace all the smiley faces. 2x. Oh, you're wondering about A. Double angle. Yes. I know. Part A is maybe the hard part, right? First semester. To remember the double angle formula?
Are we going to have to remember all the extra?
No, not really. I just, it's not the last time you'll ever see double angle identity in your life, right? I want you to know some of the more common identities. I want you to have them with you in your heart. You were hoping so. Someday you'll like it. Can someone do C for us? Or at least tell me the two values, something? Yeah, tell you want to do it? How about 6? Did I write all those down right? 0.479245, is that what you said? Okay. That's not what other people are getting? .841, is someone agreeing with that?
Yeah.
0.841 what? Okay, keep going, because they're both the same. All right, there's 3, there's 6, is that 6 sig things? Is that okay? 4, 6, 8 is the next 3 digits, is that right? And what is it the actual value of our function evaluated at? Well, I mean, let's see, it should be
0.841471.
.841471?
Yeah.
Yeah, so, I mean, the fact that this disagrees in the 5th decimal place is like, okay. Still pretty good, right? Now, again, granted, 0.5 is close to 0, so, we're going to have, if you go further away, if you try f of 1.5, these will disagree more. If you want to see how good this is actually agreeing for other x values, maybe you graph this 7th degree polynomial in one of your equations in y1 or something, and sine of 2x and y2 or something like that, and see how close this is actually getting to actually looking like the graph of sine x, sine of 2x. I think you'll be delighted to see it happening. It's fun. Anyway, so good. If you understand what we just did here, then you're doing pretty well. But are there any other questions, thoughts, comments on the homework? Especially that bottom section. The first 2 sections are pretty okay, right? You're just plugging stuff in and comparing, Phil, what do you want to do? 13. Is that cosine of root x?
Cosine root x minus 1.
All right, this is number 13. So we can use this same kind of technique we did on B. Okay, so anything else about series before we about this stuff? We want to turn our attention today to our last section, which is on math induction. And by the way, we're going to move our IB problem again, just because tomorrow we're going to need to clean up from this lesson a little bit. And I'd like to hand your quizzes back, and I'd like to maybe look at some challenge problems too. We haven't really looked at those at all, and I'd like to maybe let you have some time to work on those. So we'll do IB problem on Wednesday. And the test on Tuesday, I heard, we might have to do that on Monday or Wednesday, I think. It'll happen, the test is definitely next week. But I heard like you said a bunch of sophomores are out on Tuesday. That's like a lot of people, if it's true that half of the sophomores are going. So let me think about it.
Oh my god, I can't believe we get to go to the
Are you serious?
We got to have Mr. Martell with us and like Friday.
College fair tomorrow. So, college fair field trip.
Yeah, see if anyone else is out.
It's tomorrow. The Ivy Film. Isn't the Ivy Film on Wednesday?
Oh, yeah, tomorrow. Yeah, you said tomorrow.
Also, we never put the grade in the Ivy problem I did for comparing one.
Oh, I know. All right. So we're going to at least try and do as much of math induction today as we can. It's our last topic for this unit. And it's a little bit unfortunate. It's a little bit unfortunate to restrict us to series. We're actually going to try and show you some examples, maybe we can get to them tomorrow, of ways induction can be used for things besides series. This is a good place to introduce it, but I want you to also understand that math induction, the stuff I'm going to show you today, is much more broadly powerful than you can possibly imagine. Okay? It can be used for tons and tons of wonderful proofs. And that's what we're going to be doing today. We're going to be proving statements using a new technique that might blow your mind. It's called math induction. And before I say anything else about math induction, I should say it's different. I know you've maybe heard the word induction before with a lowercase I. It's the kind of thing that you might have heard about in science class, right? Like, we think this is true because we've gathered lots of evidence, and so it supports this conclusion. We're fairly sure. No, when we're done with math induction with a capital I, math induction is a different thing. We are going to be deductively certain of our result, right? This is actually a subset of deductive logic, okay? So when you're done, it's not like we're going to be like, oh, this result has been kind of established. No, no, the result we established today will be established, right? Never to be torn down. So this is the kind of statement that everyone proves first day when you're doing an inductive proof for the first time. The kinds of statements that you'll prove using induction are ones that are like this. For all n natural numbers n, right? Statements like that. So you can see that this is going to be a powerful thing once we prove these. Statements that are true for all natural numbers, or sometimes later you might do for all integers even, or something like that. But today we'll often be doing it for all natural numbers. So that is, for us, for 1, we'd like to prove this is true for 1, and for 2, and for 3, ad infinitum, right? This is the kind of statement we want to prove, and we'll do it in a minute. We will prove this statement in a minute using induction. But before we even go to prove these results today, we should stop, because some of the induction proofs that I'm going to give you, the results themselves are quite fun and interesting and startling. We are going to prove this, but let's just step back and appreciate what this statement says. Is this really true? Do you see what it's saying? That the sum of the first n odd numbers is n squared? Isn't that really beautiful? Certainly add up the first one. 1 squared is 1, so that's not very startling. But 1 plus 3 is 1 plus 3 plus 5 is. Does that happen always? I mean, we're going to prove that it does. Okay, but it's amazing, right? It's amazing. Some of the other results you'll see in the things we might prove are also somewhat amazing. So don't ever lose sight of the beauty too. We're going to prove some cool stuff. Yeah.
Wouldn't it be easier if it's an 2n plus 1 if you started at n equals 0?
You can do whatever you like. Doesn't matter. And then it wouldn't be n squared though. Because if you shift indexes on the left, you've got shift indexes on the right.
You start 0 instead of 1, and you change it to you still have a lot of numbers.
Well, then what's the sum of the first 0 terms? The sum of, if n is 0, what's the sum? 1. But this would say 0, wouldn't it? So your result would be wrong unless you also adjusted the right side.
Oh, yeah.
That's what I'm saying. Okay. This is a perfect candidate for math induction, so that's what we're going to do. But this particular one could actually also be proved using other, actually maybe easier methods. This particular problem. So I'm not going to tell you, but you see if you can think about other machinery you know and love, and you can maybe prove this another way. Okay. So here's how a math induction proof goes. Every math induction proof has 3 steps. Are you ready? 3 easy steps. Number 1, verify the statement is true for the base case, or the initial case, the very first value, whatever it is we're trying to start with. Up here, if we're talking about natural numbers, then show that it's true for n equals 1, right? And in fact, here, there's almost no work to do. We already said it, didn't we? Is it true if n is 1? Add up the first term. Okay, I got 1. Compute the right side. 1 squared, is that 1 also? Yay, okay. Good job. So that's kind of dumb, but we have to do it, and you'll see why soon. Step 2 is that we assume the statement is true for some number. Let's call it k. We don't want to stick to a particular number, but let's assume it's true for some k value. And the reason I'm using a different letter than n is I want to emphasize that we are not assuming the actual statement is true. We're just assuming that it's true. Let's just pretend it's true for one particular value of n. Call it k. You with me? That's a big assumption. We could be wrong, right? Let's just be clear. This could be wrong. This is either true or false, but let's assume it's true, okay? And then step 3 will be, this is called like the inductive step, is we're going to try and prove that it's true for the next number, right? So if we assumed it's true for some value, let's call it k, and our goal is to then prove that it's true for k plus 1, for the next case after the one we assumed, right? And what we've done is really, this is kind of stuck in, this is all complicated to say maybe, but really what we've done is we've said between steps 2 and 3, we've established what's called a hypothetical syllogism, right? We've said if it is true, we do not know, it may be false. If it is true for one number, then it must be true for the next number. You understand? So if someone comes along and says, so I have a proof that like, if you were to come and tell me that it's true for 50, then by my little proof, then I would know for sure that it's true for 51. Do you understand what my proof does? Okay? I do not know though whether it's true for 50 or not. But then what happens if someone comes along and tells me, hey, I actually checked it. I actually added up the first 50 odd numbers, and it was in fact 2,500. Yay! Oh, and I'm like, okay. Well then if that's true, then what must be true by my little proofs? It must be true that it's true for 51 as well. But what, wait a second. You see what's happening here? If it's true for 51, then it's got to be true for 52. N equals 52. You see how this is happening? Well, but wait a second. If it's true for 52, then it must be true for 53. So up here, this is actually kind of critical, this first step, right? This is like the A. If it is raining, then I will take an umbrella. Am I going to take an umbrella? Well, I don't know. I don't know. But if someone comes along and says it's raining, then I do know. I am going to take an umbrella. I don't know if you took an umbrella this morning. But maybe you did. But okay. But right. So this establishes like the premise as being a true statement, and then we have this hypothetical syllogism, and therefore we can conclude B, and we can keep doing it. It's like dominoes, right? If it's true for one, once you establish this, it seems so simple. Once it's true for one, it's got to be true. If this proof we established is true, then it's got to be true for 2. If it's true for 2, then it's true for 3. If it's true for 3, then it must be true for 4. See how this is going to play out? Yes, David.
In this specific scenario, can you prove that it's true for k minus 1, therefore, and then prove that it's true for k?
Yeah, there are lots of other spin-offs on induction, and this is the only version we're going to talk about. Like, yeah, you might wonder, how would you do this if you wanted to go backwards or forwards, you know?
No, just do the math with that, but k minus 1, then k plus 1.
Oh, you mean like do k minus 1 and then here k?
Yeah.
Oh, yeah. That's fine. I think that the math will be basically the same.
Yeah.
Actually, I don't think you'll see much advantage in doing that specifically. But you can do it that way, whatever. All right, so let's actually prove this statement. This is the same one I had out earlier, so let's actually prove it now, following the easy 3-step process. Okay, so here we go. This is our proof by induction. Okay, step 1, verify true for n equals 1, which is the first case, right? We're natural numbers. So we can do that. That's pretty easy on this particular problem. LHS is equal to 1, which is equal to 1 squared, which is equal to the right-hand side. The left-hand side is equal to 1, which is equal to 1 squared, which is equal to the right-hand side. So we're done. Okay, so that was not hard. And then number 2, we're going to assume true for some particular value of n. Let's call it k. That is, what are we assuming? That is, assume that for some k value, 1 plus 3 plus 5 plus ... plus 2k minus 1, I'm just rewriting the first statement up at the top, equals k squared, with a k instead of an n, right? That's what we're assuming, okay? We're assuming that this is true. It's a big assumption. Could be wrong, right? We have no idea. But let's just say that it's true for some particular k value. All right, and then our goal is to prove that it's true for n equals k plus 1, the next number. Okay, and when we're done with this, we'll have a proof that says if this is true, then it must be true for k plus 1, right? That's the domino piece that we want. That is, we want to prove that 1 plus 3 plus 5 plus ... plus 2k minus 1 plus 2 times k plus 1 minus 1 equals k plus 1 squared. Okay, let's stop and swallow that for a second. Is that okay? Is that clear in your minds what we're trying to prove? This time what I did is I took the original statement, instead of k, I plugged in for n, k plus 1, right? So instead of n, I have k plus 1 squared. I have 1 plus 3 plus 5, all the way up to, instead of 2n minus 1, I have 2 times k plus 1 minus 1. But let's just be sure you understand. The previous term is this one here, isn't it? Okay. Okay. Everyone stare at that for a second to make sure. That's what we're trying to prove. We're going to try and prove this statement. Okay. So here I go. The left-hand side is, I'm just going to copy it, 1 plus 3 plus 5 plus ... plus 2k minus 1 plus 2 times k plus 1 minus 1. Okay? And again, we can't, just like any proof, like back when we were doing trig identities or any other type of proof we've done this year, right? You can't assume that this is true, so you can't like start, this is not an equality. You can't like start subtracting things on both sides or do anything like that, right? Because this equality is not something we've established, right? We don't know yet, right? So I'm going to work with the left-hand side, just like I would have had you do with trig identities or something like that. Take the left-hand side and do stuff to it until we get the right-hand side, right? That's the way to prove it. In particular, what do you see? Anyone have an epiphany? Again, the thing we're allowed to use when we're proving this statement is the fact that this is true, right? Inside the proof, we're allowed to use this assumption. I'll call on you in a second, Ryan. I want to give everyone else a second to stare at it too, see if anyone else can have the epiphany. Other people having the epiphany? You having the epiphany? Come on, guys, have an epiphany. Go. Just do it. Okay, Ryan. We're ready. Did you have the epiphany? If it's real, again, big if, big if. If up in 2, that's true, then we can replace this section with k squared. Big if, big if. But if this is true, then this must be true. This follows. What is that, 2k plus?
Yes, that's it.
1, 2, yeah. All right. And yeah, let's drop those parentheses because they're distracting me. Oh my goodness, this proof is nice. This first one's not bad at all. What does that equal? K squared plus 2k plus 1? It's so exciting, you just can't wait. K plus 1 squared, which is equal to the right-hand side. So what have we done? Let's just make sure we're clear, because this is like feels like magic. What we've done is we've just showed that if, again, big if it's true for k, then it must also be true for k plus 1. And then, again, here comes the person with number 1 up here at the top. Someone says, hey, it's true for n equals 1. Well, we just established that it must be true for 2 as well then. And if it's true for 2, then it's true for 3. Boom! Take this thing out. Taylor has a question. Instead of what? Well, I mean, if you could just straight up prove it for k, then like you'd be done, right? You don't need induction probably. But how would you prove this without doing this kind of approach? That's nice. Do you have a way? I don't know. I guess actually there is maybe a nice way to do it. So in conclusion, right? I would like you to write something in conclusion down here. So just to like not leave people hanging. Did we do it? What did we do? So the original statement is true. For all n in the natural numbers by induction. Yay, right? If you like QEDs, you can put a QED. That's where it goes. Here. Yeah.
So what I'm saying is if you put, if you said n equals k minus 1, then the entire thing is k minus 1 is equal to So it's basically the same. Like
So you get a k squared over here.
And you put in k squared over the other term.
And over here you'd get,
K minus 1 squared plus 2k minus 1.
you get 2, yeah, I'm curious to see how that would come out. So you get this plus 2k minus 3,
No,
2k minus,
So it would still be k, so the 2k minus 1 plus k minus 1 squared, so that's k squared.
yeah, but don't you have a 2k, isn't this statement 2k minus 3 equals k minus 1 squared?
Yeah,
Okay, so then you have a k minus 1 squared you have to multiply out, right?
yeah.
Okay. I think it's an equal amount of work,
Yeah.
right? I don't know. Doesn't matter. You may do it that way if you want. All right, let's do another one. Well, first of all, everyone okay with that? Anyone still have a lingering question? Because what we've done is pretty powerful and crazy. Okay, so it's okay if you have a question. It's your first inductive proof ever in your whole life, maybe. Okay, go ahead. Yeah, I mean, you wouldn't necessarily have to, but I think that helps. It is certainly true that anyone, regardless of whether they're in this pre-calculus class or whether they're like a mathematician in, Tibet or something like that, everyone knows what to expect if you say, I'm about to prove this by induction. They're expecting these 3 things from you. Everyone in the math world knows.
So you have to verify true.
I mean, you don't have to write in exactly these words, but you definitely need to tell people what you're doing, right? Yeah, don't just write this, right? Say something like, hey, we need to verify the base case, or, we need to show that it's true. We now show that it's true for n equals 1. Or, whatever fun, smart-sounding language you want to use. But let's use English words here, okay? Because what we're doing is communicating truth. Don't just verify the algebra, right? Although that's going to be important. The algebra is going to be an important piece, of course, right? But I already know it's true, right? Because I told you. I mean, this is true. The point of a proof is to communicate truth, right? It's not to like do a little scrawling algebraic exercise. Make sure your handwriting's neat and that you're communicating, right? You're using words like so and commas and by induction and stuff like that. Okay. So let's try another one. I'm trying to make this one as similar as possible. The algebra might be a little messier, but again, stop and stare at this for a second. We're going to prove it, but also just realize how cool this is. What a cool result. If we establish this as being true, what we have is a formula for the sum of the first n squared numbers. Cool. The sum of the first n squared numbers. You want to add up perfect squares? This guy is going to do it for you. All right, pretty cool. Pretty cool. All right, so actually the very first step is a little more complicated, but not too bad, right? All right, so the left-hand side is 1 squared. Is the right-hand side, which is equal to 1, is the right-hand side come out to 1 as well? If you plug 1 in for n in the right side? So that's a little bit harder to see, isn't it? But you'll get 1/6 times 1 times 1 plus 1 plus 2 times 1 plus 1. Yeah, let's just verify. That's 1 times 2 times 3, which is 6, divided by 6, which is 1. So that works, okay? All right, and then we're supposed to, let's assume is true for some k. That is, assume 1 squared plus 2 squared plus 3 squared plus ... plus k squared equals 1/6 times k is k plus 1 is 2k plus 1 for some k. All right, and then we claim, and we're going to show, we're about to show that 1 squared plus 2 squared plus 3 squared plus ... plus k squared plus k plus 1 squared equals 1/6. Now, this is a little messy here, plugging k plus 1 everywhere, but k plus 1 times k plus 2 times 2k plus, if we plug in k plus 1 there, 2k plus 3, right? All right, so that's what we claim. We're about to prove, that's what we'd like to prove. So here we go. Let's stop there and take a breather for a second. Everyone clear on the goal? We're going to assume this, and we're going to try and prove this. It's going to feel similar to the last one. And many respects. Anyone need to stop and get off? Okay, pretty good. All right. Okay. I mean, you feel free to race ahead of me if you think you see where we're going. The left-hand side, I'm going to do basically the same thing we did last time. 1 squared plus 2 squared plus 3 squared plus plus k squared plus k plus 1 squared equals. And again, I'm trying to make, what am I doing? I'm trying to make the left side, which I just wrote down again for a second time. I'm going to try and work with it. One thing I'm allowed to do is use the assumption from 2. And eventually I'd like to get to this. 1/6 times k plus 1 times k plus 2 times 2k plus 3. Okay, so what's the power play? This is the big power play. And then there's still more work, but this is the big power play. Someone do it like we did in the last one. Not David, though. Ryan, go.
We replace that 1 squared plus 2 squared with 1/6 k times k plus 1 times 2k plus 1.
Beautiful.
We add k squared plus 1 squared to that.
Right, so that's that piece, and then we still have this k plus 1 squared. Yeah.
And then we just try to re-express that as the...
Yeah, and then we try and get that hopefully to look like this, right? So there's still like an algebraic task ahead of us, isn't there? But at least it's like meant, as far as like the scope of the problem goes, I think we've expressed it in a way that might seem more manageable. Can we get this to be like this? Well, can we make those two things equal? One way to do it, which would work and would be correct, but very time consuming and very error prone, would be to actually multiply all of this out and multiply all this out and see that they're the same. Good job, but we're repetition, we're lazy. You have a tip for us, Manoj?
Should you factor k plus 1 out?
Yeah, we should have the urge to like do whatever lazy work we can, right? Exactly. Let's factor out the k plus 1, please. Don't you have, even if you didn't know where we were headed with this, I hope you had that urge. Okay, absolutely. Let's factor that k plus 1 out so that we're left with, over here, 1/6 times k times 2k plus 1. And over here, we still have a k plus 1. Okay, that's progress as far as I'm concerned, because in its final form, I'd like it to be factored and have a k plus 1 in that factorization. Yay. In fact, I'd also like there to be a 1/6, so I'm going to do the following crazy thing. I'm also going to factor out the 1/6. No one in their right mind would ever normally do that, right? But because I already have the end in mind, right, I'm going to factor out the 1/6 as well, because I'd really, really like this to look like this result, right? When I do that, I get k times 2k plus 1. Now help me out here. If I factor out a 1/6 out of something that doesn't have it really, what is that going to be? Yeah, it's a 6 times k plus 1. If you don't believe the people who are saying this, then just multiply the 1/6 back in and see that, in fact, we haven't lied to you, okay? Everyone okay with that crazy, weird step? It's going to help you, though, I promise. And then we're hoping, keeping the end in mind, we're hoping that this equals what? What are we hoping that this thing in the parentheses equals?
K plus 2.
It does it?
Yes.
All right, so we still need to write a little conclusion, right? But if you factor this, you do get the thing we wanted. Ah.
This moment. Disappeared.
2k, oh, k plus 1. I don't know what's wrong with my board here. All right, so write some kind of conclusion at the end, but that's the idea. It's just book homework tonight. We didn't get quite as far as we would have liked, but 2 examples, that's good. That's good. We'll do more tomorrow. Have a great day.